Hello, I welcome you all to your own channel MSK Learnium. This video gives you the information that how to solve the numerical problem which is related to the Otto cycles, right? So Otto cycle is also known as the petrol cycle. In that we have a four process. Two are the isentropic, compression and expansion, and heat supplied and heat rejection at constant volume. So related to that we have a one work example. We will see an engine operating on the air standard Otto cycle. The conditions at the start of the compression at 27 degrees centigrade and 100 kilopascal. The heat added is 1840 kilojoule per kg. The compression ratio is 8. Determine the temperature and pressure at each point in the cycle, thermal efficiency and the mean effective pressure. So this is what you have a question is given. Means you have a Otto cycle in which the air is entered into the combustion chamber at certain pressure and temperature. The heat addition value is given, compression ratio is given. You have to find out the first pressure and temperature at each point, and then also you need to find out the thermal efficiency and mean effective pressure. So for that we will draw the TS diagram and then we'll see how the Otto cycle is working. So our solution is, first of all we will write down the given data. So the given data is an engine operating on the air standard Otto cycle condition at the start, means that T1 is equal to 27 degrees centigrade, means 27 plus 273, it is 300 Kelvin, and P1 is equal to 100 kilopascal, right? We'll leave it in kilopascal only. The heat supplied or heat addition, you can say QS is equal to 1840 kilojoule per kg. The compression ratio means RC is equal to 8. We have to find out the pressure and temperature at each point and thermal efficiency. So first of all what I'll do, I'll draw one TS diagram and then you can easily understand the concept, right? So here that temperature we are taking on y-axis and entropy we are taking on x-axis, right? So first of all you have a compression 1 to 2. This is 1 to 2 is the adiabatic compression, and then heat supplied at constant volume. Again you have a 2 to 3 is the heat supplied at constant volume, and then adiabatic expansion, and 3 to 4 you have a heat rejection at constant 3 to 4 is the adiabatic expansion and 4 to 1 is the heat rejection at constant volume. So this is what you have a compression 1 to 2, 2 to 3 heat supplied, 3 to 4 expansion, and 4 to 1 heat rejection. So you can say here this is the Q supply and this is the Q rejection, right, at the volume constant, and here also volume constant. So you have to find out the temperature and pressure at the each point, means T2 P2, T3 P3 and T4 P4 we have to calculate, right? So first of all what I'll do, I'll take the 1 to 2 process, 1 to 2 process, right? So 1 to 2 means T2 by T1 is equal to V1 by V2 to the power of gamma minus 1, right? That thermodynamic relation you know. So T2 we can get now, T2 is equal to, I can say T1, V1 by V2 is nothing but the RC, right? That is compression ratio to the power gamma minus 1. So air is entered into the combustion chamber. It means that for air the adiabatic constant or the ratio of a specific heat is a 1.4. So T2 we can get that T2 is equal to T1 means 300 and compression ratio is 8 which is given, and gamma is 1.4, 1.4 minus 1 is 0.4, right? So you will substitute and you will get the T2 value. So T2 will get in 680.2 Kelvin. So at the end of compression we got the temperature. Now we have to find out the pressure. So you know the 1 to 2 is the adiabatic compression. It means that PV to the power gamma will follow, right? So here you can say P1 V1 to the power of gamma is equal to P2 V2 to the power of gamma, right? Why? Because compression laws follow the adiabatic PV to the power gamma law will follow, right? So you have to find out the P2. That means P2 is equal to P1 times of V1 by V2 to the power of gamma. So P1 you have 100 kilopascal is given, and V1 by V2 is nothing but the 8 to the power of 1.4. You'll simplify, you'll get the P2 value, right? So P2 is nothing but 1837.9, 1837.9. This is also in kilopascal. So we got the P2 also. Okay, now you need to find out the T3 and T4. Okay, so T3 how we calculate that I'll tell you. So first of all we'll calculate the P3, right? So for P3 you can see here that 1, 2 to 3 is the constant volume, means the volume and temperature are related to like this. So you can say again, go to the 2 to 3 process. Okay, so we can say 2 to 3 process. So 2 to 3 process means what? That is volume is constant. So when the volume is constant, it means T3 by T2, volume is constant means P2 by T2 is equal to P3 by T3. Is it or not? Now again we can say here that we have a P2, we have a T2, we don't have P3 and we don't have a T3. But you know the what is called heat addition. Heat addition value is given. Heat addition, heat supplied is equal to what? CV into T3 minus T2, right? So here heat addition is given 1840. CV value you can take 0.718 for air, and T3 minus T2. T2 you have calculated, which is 680.2. So 680.2. When you simplify this, you'll get the value that, let me do this, 1840 divided by 0.7. So your temperature will be, that is 3242. So T3 is equal to 3242.87 Kelvin, right? So T3 we got. Now we can get the, from this relation, P3 we need to find. So P3 is equal to, we can say P3 is equal to T3 times of P2 by T2. Okay, T3 is equal to P3 is equal to T3 times of P2 by T2. P2 you don't know. P2 you know. P2 you calculated, which is 1837. So we can substitute T3 is 3242.87 into 1837.9 by T2 is 680.2. Okay, so we can simplify. So this is what we get the pressure, that is 8762, right? So 8762.24. This is also kilopascal. So P3 we got, let me check this. Yes, so this is what we got, the P3. Now we have to find out the P4 and T4, right? So again P4 and T4 means 3 to 4 process we will see, right? That is expansion. So we can say that is T4 by T3 is equal to V3 by V4 to the power of gamma minus 1, right? So but you know the V3 is equal to yes, 3 to 4 na adiabatic expansion. So V3 is equal to V2 and V4 is equal to V1. So this we can say T4 is equal to T3 times of V3 by V4 to the power of gamma minus 1. So V3 is V2 and V4 is V1. But you know V1 by V2 is equal to RC. So V2 by V1 is equal to 1 by RC. It means this value you can get T3, we can substitute T3 to 42.87, and this is 1 by 8 whole power gamma minus 1, means 1.4 minus 1 is 0.4. So you will get the value So you have a T4 is equal to 1411.54, right? So this is what you got the temperature at the end of the expansion. Similarly, you can get the P4. That P4 is what? Expansion. So you can say P3 V3 to the power of gamma is equal to P4 V4 to the power of gamma, right? So P4 we can get, P4 is equal to P3 times of V3 by V4 whole power gamma. Alright, so P3 we already calculated, which is 8762.24, and V3 by V4 is nothing but the 1 by 8. Okay, 1 by 8 whole power 1.4, gamma is 1.4, so you can substitute 8762.24 1 by 8 whole power 1.4. So your value is P4 is equal to 476.74, right, kilopascal. So that P4 also you calculated. It means that we got the temperature and pressure at each point, right? So T1, T2, T3, T4, P3, T4, P4 we got. Now we have to find out the thermal efficiency. So thermal efficiency of an Otto cycle, you know, that is 1 minus 1 by RC to the power gamma minus 1, right? So we can simply say that thermal efficiency, right? So first we'll calculate the thermal efficiency. Okay, so thermal efficiency is equal to what? That is neta Otto, thermal efficiency of Otto cycle, right? Otto cycle. So neta Otto is equal to 1 minus 1 by RC whole power gamma minus 1. So you have a 1 minus 1 by RC is given 8, and adiabatic index for the air is 1.4. So this is 0.4. So you'll get the value, that is 0.565, or you can say 56.5%. So this is the thermal efficiency of Otto we got, right, for the given questions. Now next you have to find out the mean effective pressure. So for that, first of all we need to calculate the net work. So also you know the general equation is what? That general efficiency is nothing but W net, right, by heat supplied. So if I want to know what is the net work done in this system, that is W net is equal to Otto efficiency into heat supplied. So Otto efficiency is what? 0.565 we got, and the heat supplied we are doing 1840, right? 1840. So this much of work is done, that you can say 1840 into 0.565. So this is your 1039.6 kilojoule per kg. This much of net work we calculated. Now you know the mean effective pressure is what? Mean effective pressure is nothing but the net work by swept volume. Swept volume is V1 minus V2 we can say, right? So here we'll take the first V1 we have to calculate, right? So V1 is equal to what? V1 is equal to gas equation you can use, PV is equal to MRT, M is 1. So we can say MRT1 by P1, right? Since that for better understanding, you know the PV is equal to MRT, right? So V is equal to what? MRT by P. So for V1 is equal to MRT1 by P1. So M you can take, that is R you can take as 0.287, right? 0.287 into temperature is what? 300 Kelvin by pressure you have a is 100 kilopascal, right? So you got the value, just wait, 0.287 into 300 by 100. Yes, so we got this, that is 0.861 meter cube per kg, right? Volume we got. Again you know the V1 by V2 is equal to what? Compression ratio, that is equal to 8. So V2 you got, which is 0.8661 by 8. So answer divided by 8. So this is your V2 you got, that is 0.1076 meter cube per kg, right? Now you need to find out the mean effective pressure. So you can make subheading, that is mean effective pressure, right? So mean effective pressure is what? That we are denoting by PM. We can say W net by swept volume, by swept volume. So W net is what? W net only, and the swept volume is nothing but the V1 minus V2. So you have a values is you calculated. W net is how much? That is 1039.6 by swept volume, you can say 0.861 minus 0.1076. So let me do that. 1039.6 upon 0.861 minus 0.1076. So the mean effective pressure is, you got this 1379.9 kilopascal, right? So this is how you can find out the thermal efficiency and the mean effective pressure of a given Otto cycle. So this is all about the today class. Thank you.